Hello everyone, here I want to solve the question about MIPS assembly language. So MIPS assembly is corresponding to low-level languages. Before, when I was talking about languages, they were about high-level languages like Java, C, etc. So, but also there is another type of languages like machine language, where there are just only two uh, digits to work with, 0 and 1. All right, so here we have a question. Assume that we have two registers S0 and S1. They are written in hexadecimal version and you have three arithmetic and logical instructions: add, and shift left. So let me briefly explain you what is this about. So why do we have three registers in the first add instruction? The last two registers, they make operation together, uh, like this, and they are called sources. And we transfer our source to the destination A0. Same with AND and shift left. All right, let's start. So the first one is about summation. So let's sum them. A, B, C, D, E, F plus. So as you remember, in one of our videos, we talked about summation of hexadecimal numbers. So same thinking here. But let me ask you the question, why I didn't write 0x, 0x? Because 0x is the representation, or in other words, prefix of hexadecimal version. It means that registers are written in hexadecimal. Alright, so let's start. F plus A. So F is 15 plus A, 10. It can be rewritten as 16 plus 9. So we have to write 9 here and you have carry 1. So E is going to be about F. So F plus F, that is 15 plus 15. In other words, 16 plus 14. 14 was, as far as I remember, E, and we have carry 1. So D is going to be about E with carry because it was carry 1, right? So E plus 8. What was E? It is 14. So 14 plus 8 is same thing as 16 plus 6. So 6 is written here and you have carry 1. All right. C is going to be about D. So D. Wait, am I sure about it? Like C means 12. So 12 plus 1 is going to be 13. So 13 plus 8 is the same thing as 16 plus 5. So 5 is written here and we have carry 1 here. B is 11, right? So 11 plus 1, 12. 12 plus 3 is 15. 15 is F. 11 plus 3, 14. So it's going to be E, right? So A plus 7. A plus 7 is same thing as 16 plus 1. So we have to write 1 and we have carry 1 here. And 11 plus 7 is the same thing as 16 plus 2. So we have to write 2 here and have carry 1. But let me tell you something. You know, each of our registers is written in volume of 32 bits, right? So if we work with 32 bits for the first, second register, so the resulted register, I mean destination, should be also in 32 bits. It doesn't have to exceed. So we don't have to write 1 here. That's our answer for the first instruction. Okay, let's go to the second instruction. And do you remember discrete computational structures when we were working with Boolean values like true and true is equal to true, true and false is equal to false, and false is equal to false, right? So same thing in here, but we work with binary representation. So S0, S1, all right. So what was A? 1010 1010 B. What was B? 1011 C. It was 1100 D. 1101 E. 1110 and F. 1111. So 7. It was 0111 3 0011 next 1000 and A 1010. All right. So let's compare them. 10 gives us 0, 111, 100, 111. Here 0, 111, 0001, 0001, 1100, 1100, 0100, and 0100. So that's our representation in binary, and let's convert to hexadecimal. So it is 2, 2, 3, 3, 8, 8, E, A. So in other words, register A1 is equal to 0x223388 E A. All right, and the next one is shift left. So we work with S0 again. Let's rewrite it again. So shift left means that we have to move all these numbers to the left side. So, for example, this 1111 should be somewhere starting from here. It should be like 1111. So you got my idea, right? But in order to make it easier, visually understandable, let's add 6 zeros here. And let's take each 4-bit. The first 4-bit here. Remember, it should be 32 bits in total. How many one? 1, 2, 3, 4, 5, 6. Two more. All right. Let's say write it 1010. So in hexadecimal should be A, E, F, 3, 7, B, C, 0. So you see, how does it work? So you see that our numbers S0 register was like that, right? Initially it was like that. You see this last 4 bits, 1111, this one. Or for example, can you see 1110 here? So we see that these bits are here, but last 6 digits, I mean 6 last bits are zeros because we shifted left our S0 register. All right, so A2 is equal to 0xa EF37BC0. So that's it. Thank you for your attention.